Hi, Assalamualaikum warahmatullahi wabarakatuh, and good day to everyone. Welcome to the Fluid Mechanic Laboratory. I'm Muhammad Irfan bin Ramizu from Group 3 as a leader for this week. This week, we do the experiment of flow measurement. Next, we move to the group member of this Group 3 is I'm Muhammad Irfan bin Ramizu. Next, Muhammad Afiq bin Muhammad Sabri, followed by Muhammad Haikal bin Badaruh Hisham. Then Nur Hazwani binti Muhammad Sabri, and the lastly is Cerawat anak lelaki Pranet. Okay, this is table of content for our group. First is introduction and the objective. Next is theory, followed by methodology, then result and discussion, and the lastly is conclusion. For the introduction, the fluid mechanic deals extensively with flow measurement. Chemical factories, refineries, power plants, and the other facilities that rely on exact flow rates for product quality or plant performance all employ this notion. The metering of water, natural gas, and fuel into our house and automobiles are all examples of how flow measurement are used in our daily life. In many systems, particularly when delivering fluids, it is desired and unsurprising to access integrate mass or volume. Instrument for measurement heat loss restrict to the flow and generate a pressure drop in order to get this data on flux. The Bernoulli's type device and friction loss type device are the two forms of measurement. According to the Bernoulli's equation, the total of all fluid energy along the stream is equal at every point in the constant flow because of energy conversion. As a result, the fluid speed increases while its pressure decreases. It is the ratio of discharge rate to the ideal flow rate in a stream that determine discharge coefficient. For the objective of this experiment, we compare the discharge coefficient of different type of flow measurement method. Thank you. I will pass to the next printer to continue the presentation.
For theory, many types of device using principle of Bernoulli equation has been developed to measure fluid velocities and flow rates. In this experiment, three common types of flow rate will be used, which include the orifice plate, nozzle, and venturi. The operation of each is based on the same physical principles whereby an increase in velocity results in a decrease in pressure. The description related to each of the flow meter is as follows. Orifice plate. An orifice plate is restriction with an opening smaller than the pipe diameter which is inserted in the pipe as depicted in figure 1. Due to the smaller opening area, the fluid velocity will increase and hence causing a decrease in pressure. The flow rate can be calculated from the measured pressure drop across the orifice plate. The orifice plate is the most used flow sensor, but it creates a rather large non-recoverable pressure due to the turbulence around the plate, leading to high energy consumption. With the assumption that the flow is horizontal, steady, inviscid, and incompressible between location 1 and 2, the Bernoulli equation can be applied. The following formula can be used to calculate the theoretical flow rate, can express as following. If you can see this equation 1, equation 2, and The last one is equation 3. Nozzle. With the exception of A2, the nozzle follow the same concept and calculation, equation 1 to equation 3, as the orifice plate in cross-sectional area of nozzle. The only difference between them is the geometry of the confined opening, which is approximately a quarter ellipse in figure 2. Venturi. The venturi is made up of a fast converging portion, shown as point 2 in figure 3, that increases flow velocity while lowering pressure. The diffuser is then gradually diverged to restore the pipe's original proportion. The discussed coefficient can be estimated by measuring pressure difference. Because energy loss is minimal, this method of flow measuring is quite accurate. The same assumption and calculation equation 1 to equation 3 apply to the venturi as they do the orifice plate in I, with the exception of A2, which is cross-sectional area of venturi.
Hi, it's me Haikal. For this kind of experiment, I'm going to explain and discuss more about the methodology part. As you all know, the methodology part is separate by the two parts. The first one is the apparatus part and the second one is the procedure part. So let's get started first with the apparatus part. In this experiment, we got 11 apparatus to done this experiment. The first one is multi-tube manometer. The second one is orified plate or nozzle. Number 3 is water inlet. Number 4, main switch box. Number 5, flow control valve. Number 6, venturi. Number 7, sump tank. Number 8, water outlet. Number 9, gate valve. Number 10, rotometer. And the last one is ventilation valve, the black one and the white one. The black and the white. Next, we will proceed to the procedure part. In this experiment, we got 11 steps in all of it in this experiment. So let's get started first with the first step. The first step is to ensure that the orified plate is properly fixed at its position and fasten the manometer tube H1 and H2 to the orified plate. As you can see in this picture, there is the H1 inlet here and the H2 outlet right here. So the second step is to close the flow control and the gate valve, and then turn on the main switch of the pump. Here it is the main switch and here is the pump switch. Next, simultaneously slowly open the flow control and the gate valve until they reach their maximum opening level, until the water in the manometer overflow. As you can see in the experiment here, in the picture, here is how to open the flow control valve, and the second picture is how to open the gate valve. Next, open the ventilation valve black by turning it to the anti-clockwise direction to release all the bubble if F in the system. This step is very important because it will reduce the error during the experiment. Next, the fifth step is close the ventilation valve black and then close the gate valve and turn off the pump. The sixth step, slowly open the ventilation valve, the white one, until the minimum water level of 30 to 40 millimeter is reached, and then turn on the pump. The seventh step is slowly open the gate valve until the level of water in H1 reach the maximum in 390 millimeter, and manometer H2 is at minimum level and record the reading. So as you can see in this picture, the reading of H1 is at the maximum while the reading of H2 is in the minimum. So at this state, we have to record the reading. Number 8, the 8th step is record all the reading by multi-tube meter H1 and H2 and rotometer for the Q actual for 5 different value of Q actual by adjusting or reducing the opening of gate valve. The minimum value of Q at should around 200 liter per hour. The 9th step is close the gate valve and turn off the pump. Remove the manometer tube H1 and H2 from the orified plate. So after we finish, close the gate valve and switch off the pump and the main switch. The 10th step is change orified plate with the nozzle and repeat the step 1 to 10. Meanwhile, for the venturi, the manometer tube are connected to H1 to H2, H3, and similar step of 1 to 10 are applied. As you can see in this picture, they are changing for the nozzle for the next experiment. And the last step is after finish, remove all the manometer tube from the system, close the flow control valve and turn off the pump and the main switch. So the experiment will be done. That's all for me for the metrology part.
Hi, good day everyone. I am Hazwani and I will continue with the result and also the discussion for this experiment. So as for the result, we have obtained 3 tables for the different type of flow meter, and also for the discussion, I will explain about the question number 1. Alright, so let's moving on. Okay, so here as you can see, we have the data for the nozzle. Alright, at the table we have the flow rate for the rotometer in the column number 1. We also got the volume water collected in liter, time in second, Q actual, Q theory, and height 1, which is also the differential height. And lastly, we have the discharge coefficient. Okay, as we calculated, we got the data as shown here. Okay, so next. Alright, so here are the data for the orifice plate. Same goes as before, we calculate and we got the data. Okay, next. Alright, so this is the last one, the data for the venturi meter. Alright, so for the discussion, we need to discuss the differences on water level H1 H2 in manometer with different types of flow meter. Relate your answer with pressure losses associated with the types of flow meter. Okay, as you can see, based on the result, we obtained that the value of H1 is always greater than H2 for all type of flow meter. This is because according to Bernoulli's equation, okay, so here is the Bernoulli equation, SZ1 is equal to Z2 because the inlet and outlet placed on the same height.
Hence, the Bernoulli equation is reduced into this one.
According to the equation, Q is equal to AV. Since A2 is smaller than A1, hence V2 will always be greater than V1. So as V2 is greater than V1, pressure losses is occur, which is V2 is smaller than V1. This has proved why H1 is always greater than H2. Alright, so that's all from me. Thank you.
Okay, for the second discussion is about the difference in discharge of coefficient value for each of the flow meter and the ranking of the flow meter according to the accuracy. The discharge coefficient, also known as the discharge coefficient or exhaust coefficient, is the ratio of the actual discharge to the theoretical discharge. There is a standard CD of every flow meter, such as for venturi meter, which is 0.9, for orifice plate is 0.6, and for nozzle is 0.975. To identify the accuracy, we will use the formula, which is percentage error equals to accepted value minus with average experimental value, and the result of this minus is divided by accepted value and multiply with 100%. For the third discussion, we will talk about the factor that contributing to the error or inaccuracy in experimental data and the possible recommendations to improve the existing result. For the factor that contributing to the error or inaccuracy in experimental data and the possible recommendation to improve the existing result is maybe the error occur in flow meter selection, straight run requirements, but the factor might be happen due to bad piping system, or the error also might be happen because of improper meter installation. Next, we move to the conclusion. For the conclusion, the accuracy of the 3 separate flow meter employed in this experiment was modified by the coefficient of the discharge of each flow meter. According to the experimental goal, we may conclude that the Venturi meter is the most accurate instrument based on the average discharge coefficient, which is CD. The orifice plate is the second most precise device, while the nozzle is the least precise. This is also linked to the Bernoulli equation, which describes the relationship between the rate of the fluid flow and the pressure differential between 2 points in the stable and incompressible liquid. This is the reference that we use to refer for our report. Okay, that's all from us. Thank you.